In the grand, silent theatre of the cosmos, we have long presumed to know the script. We believed the universe operated on a set of immutable laws, a celestial rulebook written in the language of mathematics and physics, observable and predictable. From the graceful waltz of planets to the fiery birth of stars, we saw a magnificent yet understandable cosmic order. But this comforting story of a knowable universe is beginning to unravel. Out in the crushing darkness, in the forgotten corners of the void and even hiding in plain sight, lie objects that mock our assumptions. They are the cosmic phantoms, the celestial enigmas, the glitches in the grand design. These are not merely puzzles to be solved. They are profound contradictions, artifacts of impossibility that have somehow found their way into our reality. They are the things that, according to our most cherished theories, simply should not exist. And their very presence whispers a terrifying and exhilarating truth. We know far less about our universe than we ever imagined. Our journey into this abyss of understanding begins in the nursery of creation itself, at the very dawn of time. For decades, our origin story has been the same. In the aftermath of the Big Bang, the universe was a hot, dense, primordial soup. Slowly, over hundreds of millions of years, gravity began its patient work, like a cosmic sculptor working with the finest dust. It pulled together wisps of hydrogen and helium, forming the first small, fragile protogalaxies. These infants then collided and merged, growing larger and more complex over billions of years, eventually creating the grand spirals we see today. This model, the lambda cold dark matter model, was elegant, supported by evidence, and became cosmic gospel. Then, humanity opened a new eye upon the universe, the James Webb Space Telescope. A magnificent golden honeycomb, it was designed to peer back into the deepest recesses of time, to capture the faint red-shifted light from the universe's first morning. Scientists expected to see exactly what the theory predicted: small, clumpy, irregular infant galaxies, the seeds of the modern cosmos. What they found instead shattered our entire understanding of cosmic evolution. They discovered galaxies that were impossibly massive, impossibly bright, and impossibly mature, shining in an era when they should have been little more than glowing clouds. Imagine an archaeologist carefully excavating a site from the earliest days of human civilization, expecting to find primitive stone tools and crude pottery. Instead, buried in the deepest, oldest layer, they unearth a fully functional smartphone. The sheer anachronism would be staggering. It would break every established timeline of technological development. This is the scale of the shock that reverberated through the astronomical community. These ancient galaxies, some existing a mere 300 million years after the Big Bang, were not small and messy. They were enormous, well-structured, and blazing with the light of stars, some seemingly even more massive than our own Milky Way is today. Our models simply cannot account for this. The universe is not old enough. There hasn't been enough time for gravity to gather that much matter, to compress it, to ignite star formation on such a colossal scale, and to feed the supermassive black holes that we now know lurk at their centres. It's as if the universe skipped adolescence and jumped straight to adulthood. This discovery is not a minor adjustment to the theory. It is a fundamental challenge. It forces us to ask terrifying questions. Was the Big Bang different than we thought? Is there some unknown cosmic accelerator, a mysterious force that supercharged galaxy growth in the early eons? Or is our entire conception of dark matter, the invisible scaffolding upon which galaxies are built, completely wrong? These impossible galaxies are not just objects. They are accusations, pointing a finger at a gaping hole in our most fundamental cosmic narrative. The universe's defiance of our expectations is not confined to the distant past. It can be found much closer to home, in the perplexing behaviour of a single unassuming star. In the constellation Cygnus, about 1,470 light-years away, lies K-EATS C84628552, more famously known as Tabby's star, named after astronomer Tabitha Boyajian, who led the study. For years, the Kepler Space Telescope stared at this star, along with 150,000 others, looking for the telltale sign of an exoplanet, a tiny, regular, periodic dip in the star's brightness, as a world passes in front of it. Kepler found thousands of planets this way, each one a predictable dimming, like a moth briefly flying in front of a distant searchlight. But Tabby's star was different. It wasn't a gentle, predictable dimming. It was a series of colossal, erratic, and deeply bizarre drops in brightness. The light from this star would plunge dramatically, sometimes by as much as 22%. To put that into perspective, a planet the size of Jupiter passing in front of a star like this would block only about 1% of its light. Whatever was passing in front of Tabby's star was enormous, or there was a vast collection of it. Furthermore, the dimming events were not periodic. They happened at random intervals and lasted for unpredictable lengths of time, from days to weeks. This was not the signature of a planet, a star, or anything known to orbital mechanics. Consider a grand, old lighthouse on a desolate coast, a beacon that has pulsed with perfect regularity for a century. Its rhythm is the bedrock of maritime navigation, a constant you can set your watch to. Then one night, its behaviour becomes utterly mad. Instead of its steady pulse, the light flickers violently, then goes out completely for 3 straight days. It returns at half its normal brightness, sputters for a week, and then suddenly flares to twice its intensity before plunging into darkness again for an unpredictable duration. An investigation would be launched immediately. You would first check the bulb and the power source. Astronomers did the equivalent, studying the star's spectrum and concluding it was a perfectly normal, stable F-type star. There was nothing wrong with the lighthouse's lamp, so you would then look for natural obstructions. Perhaps an unprecedentedly dense flock of birds. Astronomers proposed a massive swarm of comets. For this to work, thousands of giant comets would have to be disintegrating in a precise orbit to create such a massive, irregular cloud. The probability of us witnessing such a once-in-a-billion-year event is infinitesimally small. Moreover, the dust from these comets should heat up and glow in infrared light. While some infrared excess was detected, it wasn't nearly enough to account for the sheer scale of the light being blocked. Other natural explanations were proposed and discarded one by one. A planetary collision? The debris would not last long enough or be clumpy enough. Interstellar dust? It would not create such sharp, dramatic dips. After exhausting every conventional possibility, the scientific method demands that we consider the unconventional. Jason Wright, an astronomer from Penn State University, published a paper suggesting a startling hypothesis. What if the object blocking the light was not natural at all? What if it was artificial? The bizarre light curve was, he noted, consistent with what we might expect to see from a vast orbiting megastructure, perhaps a Dyson swarm, a massive collection of solar collectors built by an advanced alien civilization to harvest their star's energy. The idea was met with both intense excitement and fierce skepticism. It is a monumental claim, a solution of last resort. But the mystery of Tabby's star persists. It continues to dim and brighten unpredictably. It remains a stubborn, inexplicable anomaly, forcing us to confront a possibility that science has long relegated to fiction. The lighthouse is still flickering, and we're running out of natural explanations for who or what is blocking the light. From a star that behaves as if it is being tampered with, we turn to a visitor to our own solar system that behaved like nothing we have ever seen. For all of human history, our solar system was our celestial home, an isolated island in the vast ocean of interstellar space. We knew, theoretically, that objects from other star systems must be adrift in the galaxy, but we had never definitively seen one pass through our neighbourhood. That all changed on October 19th, 2017. The Pan-STARRS telescope in Hawaii detected a faint point of light moving at an incredible speed. It was immediately clear this was no ordinary asteroid. Its trajectory was a hyperbola, meaning it was moving far too fast to be captured by our sun's gravity. It was a tourist, a traveller from another star just passing through. It was the first interstellar object ever detected, and it was given the Hawaiian name Oumuamua, meaning a messenger from afar arriving first. But as we studied this messenger, we realised it brought with it a cascade of riddles that challenged the very definition of a celestial body. First, there was its shape. As Oumuamua tumbled through space, its brightness varied dramatically by a factor of 10. This implied it had a highly unusual elongated shape. Our best estimates suggested it was perhaps 10 times longer than it was wide, like a cosmic cigar or perhaps a flat, thin disk. No asteroid or comet in our solar system has ever been observed with such an extreme aspect ratio. Nature tends to produce lumpy, potato-shaped objects. This was something else entirely, an object of improbable geometry. The strangest anomaly, however, was revealed as Oumuamua began its journey back out into the void. Careful tracking by the Hubble Space Telescope revealed something astonishing. The object was deviating from a path governed solely by the Sun's gravity. It was accelerating, pushed by a small but persistent force. There is a known natural phenomenon that can cause this: cometary outgassing. As a comet nears the Sun, its ices vaporize, creating jets of gas that act like tiny rocket thrusters. This was the most logical explanation. But when astronomers pointed our most powerful telescopes at Oumuamua, they saw absolutely nothing. There was no fuzzy coma, no tail of gas or dust. If it was outgassing, it was doing so invisibly, unlike any of the thousands of comets we have ever studied. Let us imagine you are standing by a calm lake on a windless day. You see a piece of wood floating on the perfectly still water. Suddenly, the piece of wood changes direction and speeds up, leaving a small wake behind it. The simplest explanation is that it has a tiny, hidden motor. But you look closer with binoculars and see no motor, no propeller, no disturbance in the water around it. You then propose it must be made of a special kind of wood that releases invisible gas, pushing it along. This is a possible, if rather extraordinary, explanation. This is the position astronomers found themselves in. They had to invent new, exotic types of comets, like a solid hydrogen iceberg or a nitrogen iceberg, that could produce a powerful thrust without a visible tail. These are plausible yet completely hypothetical objects we have never seen before. Then Harvard astronomer Avi Loeb proposed a more straightforward, if more profound, explanation. He took the data at face value. The object was thin, flat, and was being accelerated by an unseen force. What if the push was not from outgassing, but from the gentle pressure of sunlight itself? For this to happen, the object would have to be incredibly thin and have a large surface area, like a solar sail. A solar sail is a form of spacecraft propulsion, a technology humans are currently developing. Loeb suggested that Oumuamua might not be a natural object at all. It could be an artifact of an extraterrestrial technology, a probe, a piece of debris, or a defunct solar sail tumbling through the galaxy, a piece of cosmic driftwood from a civilization we may never know. This hypothesis, like the one for Tabby's star, is a monumental leap. But it is a leap born from the failure of all other explanations to fit the bizarre facts. Oumuamua is gone now, lost forever to the interstellar darkness, but it left behind an unsettling question. Was our first visitor from another star a rock, or was it a message in a bottle? The universe's anomalies are not only found in active, moving objects, but also in the profound and unsettling nature of its emptiness. On the largest possible scales, the universe is not a uniform sea of galaxies. It has a structure, a magnificent architecture known as the cosmic web. Galaxies are not scattered randomly. They are drawn by gravity into colossal filaments and great walls, like shimmering threads of a spider's web stretching across billions of light years. These structures surround immense, dark, and terrifyingly empty regions known as voids. These voids are a natural part of cosmic evolution. They are the spaces left behind as gravity pulls matter together into the dense filaments. Our theories predict their existence and even their average size. But in 1981, astronomers studying a map of the heavens noticed something wrong. In the direction of the constellation Bootes, there was a patch of sky where there should have been thousands of galaxies, but there were almost none. This was not just a void, it was a supervoid, a chasm of nothingness so vast it defies our cosmological models. The Bootes void, often called the Great Nothing, is nearly 330 million light-years in diameter. If our own Milky Way galaxy were at its centre, our nearest galactic neighbour would be hundreds of millions of light-years away. From Earth, the night sky would be almost completely, perfectly black. To grasp the sheer, unnerving scale of this emptiness, imagine the universe as a vast, sprawling city at night. The galaxies are the streetlights, They cluster along highways and in downtown districts, corresponding to the filaments and clusters of the cosmic web. Between these bright areas are darker regions, the city parks and residential suburbs, which are the normal cosmic voids. The Botas void, in this analogy, is not a park. It is an area the size of an entire continent in the middle of the thriving metropolis that is utterly and completely unlit. There are no houses, no roads, no streetlights, nothing. An empty space of this magnitude should not be there. It's a statistical monstrosity. According to our best understanding of the Big Bang and the expansion of the universe, there simply has not been enough time for gravity to sweep out a region this colossal. The universe is 13.8 billion years old. To form the Botas void through the standard process of gravity pulling matter into the surrounding filaments would require much more time than has existed. It's like finding a canyon a mile deep that was apparently carved by a tiny stream in a single afternoon. The cause and the effect are wildly out of proportion. The Great Nothing is a scar on the face of the cosmos that our history cannot explain. Its existence opens the door to speculative and exotic physics. Could it be the result of a collision between our universe and another? In some multiverse theories, our cosmos is just one bubble in a larger foam of universes. Perhaps the void is the lingering bruise from an ancient impact with another bubble, an event that pushed all the matter out of that region. Or does it hint at some new property of dark energy, the mysterious force accelerating cosmic expansion, which behaved differently inside that volume of space? The Botas void is a silent testament to our ignorance. It is a place where our theories break down, a region of space that evolved illegally, defying the known cosmic statutes. To stare into it is to stare into a profound abyss, not just of space, but of our own understanding. It is the most profound kind of mystery, a mystery defined not by what is there, but by what is not. The impossibly mature galaxies of the cosmic dawn, the erratically dimming star, the anomalous interstellar visitor, the incomprehensibly vast emptiness. These are not isolated curiosities, they are a pattern. They are dispatches from the frontiers of knowledge, each one telling us the same thing. The map we have drawn of the universe is incomplete. There are entire continents of reality that remain undiscovered, governed by principles we have not yet even begun to imagine. Each of these anomalies attacks a different pillar of our cosmic knowledge. The early galaxies challenge our story of creation and evolution. Tabby's star challenges our understanding of how stars and solar systems should behave. Oumuamua challenges our conception of what kinds of objects populate the galaxy, and even the definition of natural. The Botas void challenges the fundamental rules of a large-scale structure and cosmic topography. It is as if the universe itself is actively trying to surprise us, to keep us humble, to remind us that our comprehension is a flickering candle in an infinite darkness. For centuries, science has been a process of turning monsters into mundane phenomena. Eclipses were not celestial dragons eating the sun, but the simple shadow of the moon. Comets were not harbingers of doom, but dirty snowballs on elliptical orbits. We have become comfortable in this process, confident that every mystery will eventually yield to rational explanation within our existing framework. But these objects, these things that should not exist, suggest a different path. They hint that the next great leap in understanding may not come from filling in the details of our current theories, but from a complete and revolutionary overthrow of them. We stand at a precipice, looking out at a cosmos far stranger and more mysterious than our predecessors could have ever conceived. We are haunted by the possibility of artificial structures orbiting distant suns, by the memory of a visitor that may have been a piece of alien technology, by galaxies that grew too big, too fast, and by an emptiness too profound to explain. These are not failures of science, they are its greatest invitations. They are the here-be dragons on the edge of the map, calling out to the boldest explorers. They are the anomalies that will give birth to the physics of the 21st century and beyond. The existence of these impossible things does not mean our universe is broken. It means it is bigger, richer, and infinitely more magnificent than we ever had the audacity to dream. And our journey to understand it has only just begun. What if the most profound discovery in all of human history is not waiting for us in the brilliant glare of a distant star, but is instead hidden in the profound shivering darkness of an alien sea? For millennia we have tilted our heads to the heavens, searching for messages in the starlight for signs of the others looking back. We have imagined life flourishing on worlds baked in the gentle warmth of suns like our own worlds, where water flows freely, carving canyons and filling oceans. It is a story we tell ourselves, a comforting reflection of our own existence projected onto the cosmic canvas. We search for mirrors of Earth for familiarity among the infinite strangeness. But perhaps the greatest secret of the cosmos, the answer to that ultimate question, are we alone, lies in a place we never thought to look. It resides in a realm so cold, so alien, so profoundly hostile to the very chemistry that animates you and me, that to even consider it a cradle for life feels like an act of rebellion against everything we know. This story is not about finding a second Earth. It is about the journey to a world that defies our every expectation, a world that challenges the very definition of life itself. Our destination is a moon, a giant enigmatic jewel orbiting the most magnificent planet in our solar system. We are going to Titan. Out here nearly 1 billion miles from the sun, space is vast and unforgiving. The light from our star, which bathes Earth in life-giving warmth, is here reduced to a distant, brilliant pinprick. It offers little comfort against the encroaching absolute cold. In this majestic desolation, the ringed gas giant Saturn holds, caught a colossal sphere of hydrogen and helium wrapped in bands of butterscotch and cream. It is a planet of impossible scale and serene beauty, a gravitational anchor that commands a system of over 80 moons. They swing around it in a complex silent ballet. Some are little more than captured chunks of ice and rock, pockmarked with craters from eons of bombardment. Others are more curious with strange orbits or bizarre compositions. But one of them is different. One of them is a giant, a world in its own right, larger than the planet Mercury. Alone among all the moons in our solar system, this one possesses a thick, substantial atmosphere. From a distance, it appears as a featureless, hazy orange globe, a perfect sphere of cosmic denial. There are no continents visible, no oceans, no swirling storms. There is only the deep, impenetrable, pumpkin-coloured smog. This is Titan, Saturn's veiled queen. For centuries after its discovery, it remained little more than a frustrating enigma, a world that promised so much yet revealed nothing. Its atmosphere, we discovered, was a dense shroud of nitrogen, even thicker and more pressurized at its surface than our own air on Earth. But laced within that nitrogen was a cocktail of organic molecules, carbon-based compounds, like methane and ethane. These are the very building blocks of life as we know it. The presence of this complex organic chemistry in such abundance was a tantalizing clue, a scientific siren song. An atmosphere rich in the stuff of life cloaking a mysterious surface. What wonders, or what desolation lay beneath that permanent global haze? The first robotic flybys in the 1980s only deepened the mystery. Voyager 1. Our first emissary to the outer solar system swept past its powerful cameras, straining to see. But the veil held firm. Titan simply stared back, a blank orange face, its secrets locked away. It was a cosmic treasure chest with no visible key. Was it a frozen static world, its surface chemistry trapped in an icy prison for billions of years? Or was something more dynamic, more extraordinary happening underneath that world-spanning curtain of smog? The questions lingered in the darkness for decades, a profound itch in the scientific imagination. To find the answers, we couldn't just fly by. We had to go there. We had to commit. We needed a dedicated explorer, a machine of unprecedented sophistication, designed not just to look but to see. That explorer was the Cassini-Huygens mission, a joint endeavour of human curiosity sent on a multi-billion-mile journey to settle in orbit around Saturn. For 13 years, Cassini would be our eyes and our senses in this remote kingdom of ice and gas. And for Titan, it carried a secret weapon. While its visible light cameras were as blind as Voyager's had been, Cassini was equipped with instruments that could perceive the universe in ways our own eyes cannot. It had radar capable of pinging radio waves through the thick atmosphere to trace the contours of the hidden landscape below. It had infrared spectrometers able to detect the heat signatures of different materials, painting a picture in false colour of the world beneath the haze. The mission plan was patient, methodical. With each close flyby of Titan, a new strip of the surface would be mapped like slowly assembling a 1,000-piece jigsaw puzzle in the dark. The first radar images began to trickle back across the solar system, travelling for over an hour at the speed of light to reach our receivers on Earth. And as the data was processed, as the black and white strips were stitched together, a collective gasp went through the scientific community. The image that slowly materialised on the screens was not a cratered wasteland. It was not a uniform sheet of ice. It was a landscape of shocking, impossible familiarity. We saw channels, hundreds of them, snaking across the terrain. They meandered, they branched. They formed intricate dendritic patterns that looked for all the world like river networks. We saw vast, dark, flat plains that looked unnervingly like ancient lake beds. There were shorelines clearly defined and elegant in their curves, suggesting the past presence of a massive body of liquid. There were even features that looked like deltas where a river had once deposited sediment as it flowed into a larger sea. It was a ghost of a landscape we knew intimately. It was the geography of Earth, the signature of a dynamic flowing liquid shaping a planetary surface. But this could not be. The surface of Titan is a staggering 290 degrees below 0 Fahrenheit or minus 180 Celsius. At this temperature, water is not a liquid that flows and carves canyons. It is a mineral. It is a rock as hard as granite. The riverbeds we were seeing could not have been carved by water. The shorelines could not be the mark of ancient oceans like our own. We were staring at a profound paradox, a geological riddle on a planetary scale. If not water, then what? What liquid could possibly exist flowing and free in such an unbelievable, cryogenic environment? Cassini's instruments provided the stunning revolutionary answer. The dark patches on the radar images, the smooth flat areas that absorbed the radio waves, were not dry lake beds. They were full. They were vast standing bodies of liquid. But the liquid was not water. It was a mixture of liquid methane and ethane substances we know on Earth only as gases, the primary components of natural gas. Here in the crushing cold of the outer solar system, these hydrocarbons condense from the atmosphere as rain. They flow across the surface in rivers, and they pool in enormous lakes and seas. We had discovered a world with a complete active hydrological cycle, just like Earth's, but with a fundamentally alien chemistry. Titan has clouds not of water vapour, but of methane. It has rain not of water, but of liquid natural gas. It has rivers that carve through hills of rock-hard water ice, and it has seas whose waves slow and syrupy in the cold lap against shores of frozen organic sediment. These are not mere ponds, they are true seas. One of the largest Kraken Mare is a sprawling multi-lobed basin larger in surface area than the Caspian Sea on Earth. Another Ligia Mare is a deep placid sea in some places over 500 feet deep, containing more liquid hydrocarbons than all of Earth's proven reserves of oil and natural gas combined. We have given them names from mythology, names of monsters and titans because their very existence feels like something from a legend. Imagine standing on the shores of Ligia Mare. You would be standing on a beach, not of sand, but of dark, tar-like organic solids that have rained down from the atmosphere over millions of years. The sky above you would not be blue, but a perpetual hazy orange twilight, the sun a dim and distant memory. The air thick and still would be unbreathable, a nitrogen-rich atmosphere laced with a hydrocarbon smog. Before you stretching to the horizon would be a sea of liquid methane black and eerily calm. The gravity on Titan is low, only about 1/7 of Earth's, and the liquid itself is viscous, less dense than water. Any waves that formed would be slow, majestic, lumbering giants rising and falling with a strange lazy grace. Looking down into the depth you would see nothing. The liquid is likely as dark as crude oil absorbing the faint light that filters through the hazy sky. There would be no familiar smell of salt or sea spray, only the biting chemical cold. This is an environment more alien than anything we had ever conceived. a dark, cold hydrocarbon world, yet one that mirrors our own planet in such haunting and profound ways. And it is here in this place of cryogenic chemistry and eerie familiarity that we must ask the most audacious question in all of science. Could something be alive in there? Could something actually be swimming in a sea of liquid natural gas? On its face, the idea is absurd. Life as we understand it is a celebration of water. Every living thing on our planet, from the smallest bacterium to the largest blue whale, is fundamentally based on liquid water. It is the universal solvent, the medium in which the chemical reactions of life take place. Our cells are intricate biological machines operating in an aqueous environment. We are in essence exquisitely organised bags of water. Titan offers none of that. It is a world where the essential ingredient for our kind of life is permanently locked away as frozen inert rock. The liquids that do exist, methane and ethane, are non-polar solvents. They behave in a radically different way than water. The fundamental chemistry that allows our cell membranes to form, that allows our proteins to fold, and our DNA to encode information would simply fall apart in a methane sea. By every metric we have ever used to define a habitable world, Titan is a barren chemical wasteland. It is too cold, its liquids are wrong, and its atmosphere lacks the free oxygen that fuels complex life on Earth. Yet, this dismissal is a product of our own limited experience. We are basing our judgment on a single data point life on Earth. What if this is an epic failure of imagination? What if life is not a singular miracle, but a cosmic imperative that adapts to the conditions it finds? What if there is more than one way to build a living thing? The universe is vast and endlessly creative. Perhaps, just perhaps, in the frigid dark seas of Titan, a completely different kind of biology has taken root. A second genesis. An independent origin of life that follows a different set of chemical rules. To even contemplate this, we must tear up our Earth-based rulebook and start over. We need to envision a new kind of biology, one that is not built for the warm, watery cradle of Earth, but is instead perfectly tailored for the cryogenic hydrocarbon abyss of Titan. What would its building blocks be? Life on Earth is based on the phospholipid bilayer, a clever membrane that creates a stable barrier between the watery interior of a cell and the watery environment outside. This structure would instantly disintegrate in liquid methane. But scientists working in laboratories and with powerful computer simulations have imagined a radical alternative. They call it an azotosome. It would be a cell membrane built not from phospholipids, but from small nitrogen-containing organic compounds, molecules that are known to exist in abundance on Titan. Calculations show that these azotosomes could form tiny hollow spheres that are both stable and flexible in liquid methane even at 290 degrees below zero. They could be the cosmic alternative to our own cell walls, a different solution to the universal problem of how to contain the machinery of life, and what would power such a life form. We terrestrial creatures are oxidizers. We breathe in oxygen, which we use to burn organic fuels like sugars, releasing the energy that powers our bodies. There is no free oxygen to speak of on Titan, but there are other options. Titan's atmosphere is rich in hydrogen, and a molecule called acetylene. A hypothetical titanian microbe could, in theory, breathe in hydrogen from the atmosphere and react it with acetylene, which it would consume as food. The chemical reaction would release energy enough to power a slow cold metabolism. And what would be the waste product, the equivalent of our exhaled carbon dioxide? The answer is methane, the very liquid that makes up the seas themselves. These creatures would exhale the main component of their own environment. It's an alien metabolism, a completely self-contained system that is elegant, plausible, and perfectly adapted to the strange chemical reality of Titan. So what would this life look like? It would not be like us. The energy available from this kind of chemical reaction is far less than what is available from oxygen-based respiration. Life on Titan would therefore be slow, incredibly slow. There would be no frantic chase between predator and prey, no rapid energetic movements. We must imagine creatures of a different tempo life unfolding on a geological timescale. Perhaps they would be silicon-based with crystalline structures that are more stable in the extreme cold. Perhaps they would be gelatinous, amorphous beings that glide slowly through the viscous, oily depths, absorbing their chemical food directly from the methane sea. Their senses would not rely on light. but perhaps on sonar or the detection of subtle chemical gradients in the dark liquid. The fish of Titan might not be fish at all, but something far stranger. Hydrocarbon leviathans born of cold and shadow moving with a glacial grace through the black silent seas. They would be beings whose every biological process from metabolism to reproduction would operate at a pace we would find almost imperceptible. They would be living expressions of the moon itself, slow cold, mysterious and patient. This is for now speculation. It is a hypothesis born from the tantalizing clues Titan has given us. But it's not fantasy. It is a scientifically grounded possibility that forces us to expand our vision of what life can be and where it can be found. Titan presents us with all the necessary ingredients. It has a thick atmosphere for protection. It has a rich and complex soup of organic chemicals. It has a source of energy. And most critically, it has a liquid medium vast seas where these chemical building blocks can mix, interact, and perhaps over the course of billions of years, organize themselves into something truly alive. The stage is set for a second genesis. The possibility is there, written in the chemistry of this incredible world. The question is no longer merely philosophical. It is now a tangible scientific quest. The clues point to the dark, silent depths of Kraken Mare, to the hydrocarbon shores of Ligaia. Now we must begin the search. Our challenge is to find the evidence, to listen for the faint chemical whispers of an alien biology, for the subtle signs of a metabolism that is not our own. We must find a way to look for the ghosts in this extraordinary machine, to search for alien fish swimming in the dark. What if the most profound secrets of life in the cosmos are not hidden in the gentle warmth of a sunbeam, but are instead locked away in a deep shivering cold in a twilight world bathed in a strange golden haze? For 350 years this very question haunted us, whispered from a single enigmatic point of light in the outer solar system. It began not with a fleet of starships, but with the patient eye of one man, Christian Huygens, peering through a brass and wood telescope in the flickering candlelight of 1655. Through the delicate dance of polished glass, a faint solitary speck of light revealed itself, a loyal companion to the ringed giant Saturn. He had discovered a new moon, the first of many for Saturn, but this one was different. It was substantial, it was significant, and it was for all intents and purposes utterly unknowable. What Huygens couldn't have possibly grasped was that this tiny dot, this celestial attendant, was not merely a ball of rock and ice. It was a world with a secret, a world wrapped in an impenetrable atmospheric shroud, a place that would guard its mysteries more fiercely than any other in our solar system. For the next 3 centuries, that is precisely what Titan did. It taunted us. As telescopes grew in power, evolving from simple lenses to colossal mirrors capable of gathering ancient light from the universe's edge, Titan remained stubbornly indistinct. It presented itself as a featureless orange-tinted sphere, a cosmic cipher. Astronomers could measure its size larger than the planet Mercury and calculate its orbit with exquisite precision, yet its surface was a complete and total blank. It was like trying to read a book through a frosted window. You know there are pages filled with stories inside, but the words, the characters, the landscapes are all denied to you. The frustration among scientists was palpable. Here was a world, not just a moon, with a diameter so vast and a gravity strong enough to hold on to something precious in atmosphere. Early in the 20th century, spectroscopic analysis, the art of dissecting light to reveal the chemical composition of distant objects, began to yield the first tantalizing clues. In 1944, Gerard Kuiper aimed his telescope at that frustratingly blank orb and found the unmistakable chemical fingerprint of methane gas. Methane, the simplest organic molecule. On Earth it is intimately tied to life, a byproduct of biology. Its presence on Titan was a shock, a profound suggestion that this was no inert ball of ice. It had chemistry, it had an atmosphere. But the orange haze that veiled the moon was so thick, so pervasive, that it only deepened the enigma. What could be happening beneath that global blanket of smog? What kind of world produces an atmosphere so dense with organic compounds? The questions multiplied, fueling speculation that ranged from the scientifically plausible to the wildly imaginative. Some envisioned a global ocean of liquid methane, a frigid primordial soup. others pictured a surface coated in a thick tar-like sludge of complex organic molecules, the fallen remnants of photochemical reactions high in the atmosphere. No one knew, and for decades we had no way of finding out. Our first robotic emissaries, the magnificent Voyager probes, offered us our first close-up encounter in the early 1980s. As Voyager 1 screamed past the Saturnian system, its cameras swiveled to stare at the moon that had mystified us for so long. The images it sent back across 1 billion miles of space were both breathtaking and maddening. We saw it in stunning detail, a perfect, featureless, hazy orange ball. The mystery had only intensified. Voyager's instruments confirmed the atmosphere was even denser than we had imagined, more massive than Earth's, and composed primarily of nitrogen, just like our own air. But it was the thick, high-altitude layers of photochemical smog created as sunlight relentlessly broke down methane molecules that formed the impenetrable veil. We had travelled all the way to the edge of the outer solar system only to have the door slammed in our face. We were so close, yet the true nature of Titan's surface remained as much a mystery as it was to Christian Huygens. We had traded a distant blurry dot for a close-up sharp-edged enigma. But humanity does not surrender to mystery. It answers it. In the quiet halls of space agencies in America and Europe, a new plan was being forged, a mission of such breathtaking ambition it bordered on audacity. We would not just fly by this time. We would not just take pictures of the clouds. We would go back and we would stay. We would enter into orbit, we would map the unseen, and we would do the unthinkable. We would send a probe down through the haze to land on its surface. This was the genesis of Cassini-Huygens, not just a machine, but a multi-generational promise to solve the riddle of Titan. The spacecraft itself was a masterpiece of engineering, a testament to human ingenuity. Standing over 2 stories tall and weighing more than 6 tons, Cassini was the most complex and capable interplanetary probe ever constructed. It was a travelling robotic laboratory, equipped with a suite of 12 exquisitely sensitive instruments, designed to see in wavelengths far beyond human vision, to taste the particles of Saturn's rings, to smell the composition of Titan's upper atmosphere, to feel the tug of unseen moons, and most importantly, to see through the impenetrable smog. Cradled on its side was its partner in discovery, the Huygens probe. Named for the moon's discoverer, this saucer-shaped vessel was a marvel of compact design, a heat-shielded, parachute-equipped scout built for a single terrifying one-way journey. Its mission to survive a fiery atmospheric entry at 17,000 miles per hour, descend for 2.5 hours through the alien sky, and report back on everything it saw, felt and heard before its batteries died on an unknown, unseen surface. The scale of the collaboration was as grand as the machine itself, a joint effort between NASA, the European Space Agency, and the Italian Space Agency, involving scientists and engineers from dozens of countries. For years they planned, they built, they tested, all for a journey that would take 7 years just to arrive. In the autumn of 1997, this colossal ambassador of human curiosity was perched atop a pillar of controlled fire, ready to begin its long voyage. The launch was a spectacle of raw power, a violent, ground-shaking roar that slowly, majestically lifted our questions and our hopes toward the heavens. For the next 7 years, Cassini-Huygens executed a flawless, intricate dance across the inner solar system. It was a cosmic slingshot maneuver on a grand scale, borrowing momentum from other worlds to build the velocity needed to reach the distant realm of Saturn. It swung by Venus not once, but twice, using the planet's immense gravity to bend its trajectory and boost its speed. It then flew past our own home Earth, a final poignant farewell, as it stole a whisper of our planet's orbital energy, giving humanity a gravitational high five on its way to the great unknown. Then came the lonely years, along quiet, coasting through the dark, cold expanse beyond the asteroid belt. On board, the plutonium hearts of its radioisotope thermoelectric generators glowed with steady warmth, providing the lifeblood of electricity that kept its intricate systems alive. The computers slept, the instruments lay dormant, all of it, waiting for the day it would awaken in the shadow of the ringed planet. In the summer of 2004, that day finally arrived. After a journey of more than 2 billion miles, Cassini approached its destination. The Saturn orbit insertion was a moment of supreme heart-stopping tension for the mission controllers back on Earth. For 96 agonizing minutes, the spacecraft fired its main engine, a desperate, powerful braking maneuver to bleed off enough speed to be captured by Saturn's gravity. If it fired for too long, it would burn up in Saturn's atmosphere. Too short, and it would skim past and be flung out into the void, lost forever. The commands had been sent hours before. The spacecraft was now on its own. On Earth, we could only wait for the radio signal travelling at the speed of light to bring us the news. And then it came. Success. Cassini had arrived. It was now a permanent artificial moon of Saturn, our steadfast sentinel in this majestic alien system. And its primary target, the great orange mystery Titan, was waiting. Almost immediately, Cassini turned its powerful senses toward the shrouded moon, and our understanding of this world was rewritten overnight. The first temperature readings were staggering. The surface of Titan was a mind-numbing 300 degrees below 0 Fahrenheit, or minus 179 Celsius. This was a cold so profound, so absolute, that it defies our terrestrial intuition. It is a cold where water is no longer a liquid, or even ice as we know it, but a substance as hard and unyielding as granite. On Titan, ice forms the very bedrock of the world, creating mountains and crusts as solid as any rock on Earth. The atmosphere, as Voyager had hinted, was a thick, soupy sea of nitrogen laced with that intriguing methane. But Cassini's instruments were far more sensitive. They sniffed out a veritable cocktail of complex organic molecules in the upper atmosphere: ethane, propane, acetylene, cyanoacetylene, a rich organic factory powered by the sun's ultraviolet light, and Saturn's magnetic field. This was confirmation that the building blocks of life-complex carbon-based molecules were being mass-produced in Titan's skies, raining down constantly onto the surface below. But what was that surface? What lay hidden beneath the smog? This was the moment for Cassini's secret weapon, the instrument that would finally give us sight. The radar instrument. It could not see invisible light, but it could pierce the haze by shouting radio waves at the surface and carefully listening for the echoes that returned. It was planetary echolocation, a way to map a hidden landscape by sound rather than sight. The process was painstakingly slow. On each close flyby of Titan, Cassini could only map a narrow ribbon of the surface. It would take dozens upon dozens of flybys executed over many years to slowly stitch together a global map like a patient cartographer, painting a new continent one brushstroke at a time. The first radar swathes came back to Earth, transmitted across the vastness of space to the eager scientists waiting at the Jet Propulsion Laboratory. They held their breath as the raw data was processed, translated from radio echoes into visual images, and then they saw it. The images were otherworldly, ghostly, and utterly riveting. There were vast sweeping plains that seemed to be covered in some kind of sand, but at these temperatures it couldn't be silicate sand like on Earth. The data suggested it was sand made of frozen, solid hydrocarbon particles. There were towering mountain ranges not of rock, but of solid water ice, sculpted and eroded by forces we couldn't yet comprehend. And then they saw the channels, unmistakable branching networks that looked exactly like river systems on Earth. They snaked across the landscape for hundreds of miles with tributaries flowing into main channels, carving valleys and deltas. It was the signature of flowing liquid. But liquid what? At 300 degrees below zero, it could not be water. The answer was already in front of us in the atmospheric data. The only substances that could exist as liquids in this extreme cryogenic environment were the very organic compounds Cassini had detected in the air: methane and ethane. This was the bombshell discovery, the paradigm shift that changed everything. Titan had a hydrological cycle, a complete functioning weather system, just like Earth's, but with hydrocarbons playing the role of water. High in the frigid atmosphere, methane gas would condense into clouds. From these alien clouds it would rain liquid methane. This methane rain would fall onto the surface, forming rivers that carved channels through the water ice mountains and across the hydrocarbon dunes. These rivers would then flow down into vast placid basins, forming lakes and seas. And from the surfaces of these great lakes, the liquid would evaporate back into the atmosphere to begin the cycle anew. It was Earth, but a twisted cryogenic reflection of it. We were looking at a world with rain rivers and seas made of liquid natural gas. The radar images kept coming, revealing more of this astonishing truth. The team found immense dark smooth patches concentrated near the poles features that absorbed the radar waves just as a calm body of liquid would. One was so vast it was named Kraken Mare, a sea larger than all of North America's Great Lakes combined. Another was named Ligeia Mare, a deep methane-rich sea that shimmered in the radar's eye. We had found the global oceans that scientists had dreamed of for decades. They weren't water, but they were liquid. They were vast, and they were real. For the first time we could truly see Titan, not as a fuzzy dot, not as a hazy orb, but as a dynamic living world with geology and meteorology, and a landscape of stunning alien beauty. We had peeled back the veil, but in doing so we had uncovered a mystery far deeper and more profound than we had ever imagined. We had found an environment unique in the solar system, a world with a thick atmosphere, complex organic chemistry, and stable bodies of surface liquid. 3 key ingredients that on our planet led to the miracle of biology, which forced us to ask the ultimate question. If you have rivers and rains and seas, even if they are made of methane, does that mean you can have something swimming in them? We had journeyed across the solar system to solve an old riddle, only to find ourselves standing on the shore of an alien sea confronted by a new one, the most tantalizing question of all. And so for years we waited. Cassini had become a silent partner to this veiled giant, patiently charting its gravitational wobbles, tasting the outermost wisps of its nitrogen shroud, but always denied a clear view of the surface. The Huygens probe had given us a single fleeting postcard, a tantalizing glimpse of a frozen shoreline before its brief life was extinguished. It was a clue, but it was not the answer. The grand mystery of what lay beneath the smog remained unsolved, a planetary secret locked away from human eyes. But Cassini carried a key. It wasn't an optical camera which would be blinded by the haze, but something far more powerful, a way of seeing in the dark. It carried a radar instrument, a synthetic aperture radar, designed not to look, but to listen to the shape of the world below. This instrument was our set of Promethean eyes capable of piercing the impenetrable orange veil and painting a portrait of the hidden landscape with radio waves. The plan was audacious to use these waves, bouncing them off the surface from hundreds of thousands of kilometers away, to meticulously map the geography of a world we had never truly seen. Each flyby was a carefully choreographed cosmic ballet, a high-stakes encounter where the spacecraft skimmed the atmosphere, its radar antenna pointed down into the perpetual twilight. The first few passes over the equatorial regions, the same areas Huygens had hinted at, revealed vast continent-sized plains of what appeared to be dunes. Not dunes of sand, of silicate rock, but of solid hydrocarbon grains, a desert sculpted by alien winds. It was fascinating, a landscape of immense frozen fields, but it was not the world of seas we had dreamed of. The hope, the decades-old theory of a global methane ocean began to feel like a romantic fiction. Perhaps Titan was just a dry, cold, dusty ball after all. The mission scientists held their breath. The models, the mathematics, everything had pointed to liquid. Had we been so profoundly wrong? Then on the 22nd of July 2006, Cassini's trajectory carried it over the high northern latitudes, a region of Titan locked in the darkness of its long winter. The radar began its methodical sweep, its radio pings descending, striking the surface, and echoing back up to the waiting antenna. The data streamed across the void, a torrent of numbers arriving at Earth, which computers began to translate into an image line by painstaking line. And there on the screens at the Jet Propulsion Laboratory, something entirely new began to emerge from the digital static. Patches. Dark amorphous patches scattered across the Arctic landscape. In radar imagery, darkness means smoothness. A rough cratered or mountainous terrain scatters the radio waves, creating a bright, noisy return signal. But a perfectly smooth surface does the opposite. It reflects the signal away in a single direction, like a mirror, leaving a dark, quiet void in the resulting image. These patches were extraordinarily dark. They were smoother than anything else seen on Titan, smoother than almost any natural surface in the solar system. Speculation ignited through the science teams. Could they be vast plains of water ice polished flat like a skating rink? Or perhaps deposits of organic tar settled out of the thick atmosphere? Or could they be what we had dared to hope for all along? The definitive proof the smoking gun came from a peculiar phenomenon, a quirk of physics that turned a quiet observation into a thunderous discovery. It's called a specular reflection. You've seen it yourself standing by a lake on a calm day. When the sun is at just the right angle, its reflection flashes off the water, a brilliant, blinding glint of light. A solid surface, even a smooth one, doesn't do that. Only a liquid, a substance with a perfectly flat, molecularly smooth surface, can act as a true mirror. The science team re-angled Cassini on a subsequent flyby, positioning its radar to see if it could catch such a glint. It was a long shot, a moment of pure, hopeful science. And then it happened. From a dark feature near the North Pole, the radar instrument received an impossibly bright, sharp echo. A flash of radio light 10 times brighter than the surrounding terrain. It was the glint, the specular reflection. The mirror on Titan's surface had flashed back at us. There was no longer any ambiguity, no room for doubt. It was liquid. After centuries of dreaming and decades of searching, we had found it. We had discovered the first extraterrestrial seas. It was a moment that redrew our map of the solar system. The news rippled through the scientific community, a seismic shock of confirmation. Titan was not a dead, dry world. It was alive, with a hydrological cycle so familiar it was chilling. Except here, the liquid wasn't water. It was a frigid, otherworldly cocktail of liquid methane and ethane substances we know on Earth as flammable, volatile gases. At the cryogenic temperatures of Titan, minus 180 degrees Celsius, these hydrocarbons condense into a stable, clear liquid, behaving in almost exactly the same way water does on our home planet. The discovery opened the floodgates. With each new pass over the poles, the map grew more detailed, more astonishing. The dark patches were not just ponds, they were immense bodies of liquid. We gave them names drawn from mythology monsters and mythical beasts for a monstrous and mythical sea. There was Kraken Mare, the largest of them all. A sprawling gargantuan sea so vast it holds more liquid hydrocarbon than all of Earth's oil and natural gas reserves combined. If you stood on its shore, its far coastline would be deep beyond the horizon, its surface a dark, placid mirror under the perpetual orange sky. Then there was Ligeia Mare, the second largest sea, a majestic basin deeper in some places than the Adriatic Sea on Earth. Cassini's radar was powerful enough to pierce its depths, revealing a floor remarkably smooth, covered in a thick sludge of organic material that has rained down from the sky for eons. The liquid itself, we learned, was stunningly pure, almost entirely methane, making it transparent to the probing radio waves. And Punga Mare, smaller, nestled closer to the pole, its coastline intricate and complex, hinting at a different geological history. These three great seas, the Maria of Titan, dominate the northern polar region, a trinity of liquid darkness. But the discoveries weren't confined to these colossal bodies. Scattered all around them and across the landscape toward the equator, the radar revealed hundreds of smaller lakes. Some were vast, the size of Lake Superior. Others were smaller, nestled in sharp-rimmed, steep-sided depressions, as if a giant cookie cutter had punched holes in the icy bedrock. These appeared to be karstic lakes formed when the liquid methane dissolved the ice and organic solids of the crust, causing it to collapse and form a basin, a process identical to the way sinkholes form and create lakes in limestone regions on Earth. The familiarity was unnerving. We were looking at a world 1.5 billion kilometers away, yet its geological language was one we could read instantly. The South Pole, too, held its own treasures, though on a more modest scale. Its most prominent feature was Ontario Lacus, a lone lake roughly the size of its earthly namesake Lake Ontario. And here we witnessed something even more profound than the existence of liquid. We witnessed change. Over the course of the Cassini mission, as the seasons on Titan slowly shifted, we watched the shoreline of Ontario Lacus recede. Like a salt flat on Earth, it appeared to be drying up during the southern summer, leaving behind a dark evaporate crust. We were seeing in real time Titan's climate in action. This wasn't a static frozen museum. It was a dynamic breathing world with seasons, with climate change, with a pulse that beat to the rhythm of its 29-year orbit around the Sun. Perhaps the most breathtaking revelation was the connection between these features. Winding their way across the frozen plains, emptying into the lakes and the Great Maria were river channels, hundreds of them. They were not pale, ghostly remnants of a distant past like on Mars. They were dark, sharp and fresh, many of them still filled with flowing liquid. We could see them branching into intricate dendritic networks, creating vast river deltas that were indistinguishable from the Nile or the Mississippi River Delta, if you ignored the fact that they were carved by liquid natural gas. We followed the path of one named Vid Fluminon, a river valley that meanders for over 400 kilometres, a cryogenic Nile flowing through the alien Arctic. It was the final piece of the puzzle. The cycle was complete. We had the seas, the source of the vapour. We had observed clouds, vast storms of liquid methane gathering in the atmosphere, and now we had the rivers, the arteries that returned the liquid to the seas. We had even seen the rain itself. In 2010, Cassini's instruments observed a storm system rage across the equatorial deserts, and in the days that followed, the radar image of that area showed a dramatic darkening of the surface. The ground was wet. It had rained. Imagine standing there on that frigid dune field. The sky, already a dim hazy orange, would darken to a deep bruised purple, and then the drops would begin to fall. Not of water, but of a substance colder than liquid nitrogen. A chilling, oily drizzle of methane splashing onto an ice-rich ground that is as hard as granite. This is the weather on Titan, and here is where the profound, soul-shaking challenge truly begins. We're confronted with a world that is a ghost of our own. A planet with a thick nitrogen atmosphere just like ours. A world with continents, mountains, deserts and seas. A world with clouds, storms, rain, rivers and lakes. It follows the same rulebook of geology and meteorology as Earth. Every process, from the erosion of a river valley to the formation of a coastal shoreline, is a direct, undeniable parallel to our own planet. If you were to look at the radar maps without knowing the chemistry, you would swear you were looking at a coastline in Norway, or a river system in the Amazon basin. The mimicry is perfect, but the chemistry is a fundamental heresy. On Titan, the bedrock is not silicate rock, but water ice frozen so hard it has the strength of stone. The sand in the deserts is not silicon dioxide, but solid hydrocarbon particles, and the liquid, the lifeblood of the entire system, is not water, it is methane. This single staggering fact forces us to confront our deepest, most cherished assumptions about life in the universe. For decades, our search for extraterrestrial life has been a search for water. Follow the water has been the mantra of astrobiology. It is the universal solvent, the one ingredient we believe to be absolutely essential for the complex chemical reactions that give rise to life. Water is life, we told ourselves. Titan stands in defiant contradiction to that creed. It presents us with a world where water is a worthless inert rock, and a substance we consider a simple fuel has taken its place as the elixir of geology and climate. It offers us an alternative pathway. A world where a completely different liquid with a completely different chemistry has produced the same geological and meteorological complexity as our own. And this begs the ultimate question. If methane can so perfectly replicate water's role in shaping a planet's surface, could it also replicate water's role in originating life? Could these frigid hydrocarbon seas devoid of the one substance we thought was essential be home to a form of biology we have never imagined? A life that breathes hydrogen instead of oxygen. A life whose cells are not based on a phospholipid bilayer which would dissolve in methane, but on something far stranger, an azotosome perhaps. A life whose very metabolism would be anathema to our own thriving in an environment that to us is a deep-freeze toxic wasteland. This is the paradigm shift that Cassini's radar delivered. The question was no longer just, is there life beyond Earth? It had become something far more subtle, far more profound. The question was now, what do we even mean by life? The stage was set. We had discovered the theatre of this alien world. We had mapped its strange dark oceans and its methane rivers. Now we had to look deeper past the geography and into the chemistry to see if within these cryogenic waters an entirely new story of biology might just be waiting to begin. And so we are left adrift on this impossible sea, a silent, frozen world awash in liquid natural gas. The engineering of Titan, its sheer alien architecture, defies every instinct we possess. We have followed the rivers, charted the coastlines, and measured the depths of these methane oceans, only to arrive at a profound and intimidating silence. The question which has been a gravitational whisper in the back of our minds since we first saw those dark reflective patches now thunders with undeniable force. How in this cathedral of cold could the spark of life possibly ignite? To even begin to answer, we must perform a difficult, almost heretical act of imagination. We must dismantle the very definition of life itself, taking it apart piece by piece, and see if we can reassemble it using Titan's strange and frozen toolkit. On Earth, the story of biology is inseparable from the story of water. It is the matrix, the stage, the universal solvent upon which our entire epic has been written. A water molecule is a chemical marvel, a tiny magnet with a positive and a negative end. This polarity allows it to embrace other molecules, to pull apart salts, to cradle complex proteins, and to ferry nutrients into the deepest recesses of a living cell. It is this unique ability to form and break hydrogen bonds that gives water its remarkable properties, allowing it to remain liquid across a generous range of temperatures and to act as a superb thermal regulator, protecting fragile organic structures from a planet's fickle climate. Every living thing you have ever seen, from the bacteria in the deepest hydrothermal vents to the cells that make up your own body, is fundamentally an aquatic creature, a sophisticated bag of water animated by chemistry. Our biology is so exquisitely tuned to its solvent that we find it nearly impossible to conceive of an alternative. But on Titan, under that thick orange sky, we have no choice. There, the universal solvent of Earth is nothing but bedrock frozen harder than granite. The liquid that fills Titan's basins, the methane, and ethane is the chemical opposite of water. Methane molecules are nonpolar. They have no magnetic hooks, no charged ends to grab onto other substances. They are chemically aloof, interacting with the world through forces that are profoundly weak and indifferent. In this frigid nonpolar sea, the chemistry we know would simply fall apart. Our kind of life, if plunged into a lake like Kraken Mare, would face a crisis more fundamental than the cold. Its cellular machinery would grind to an immediate halt. The delicate water-loving proteins that perform the miracles of life would twist into useless shapes repelled by the alien liquid around them. The very boundary separating life from non-life, the cell membrane, would disintegrate. On Earth, this membrane is a bilayer of lipids molecules with water-loving heads and water-fearing tails. In water, they spontaneously arrange themselves into a perfect sphere, tails tucked inward, creating a stable, waterproof barrier. But in a methane sea, this elegant structure would turn against itself. The water-fearing tails would eagerly reach out to embrace the surrounding methane, while the water-loving heads would huddle together in terror. The membrane would invert, exposing the cell's precious guts to the hostile environment, a complete and instantaneous biological failure. This is not merely a problem for earthly life. It is a fundamental challenge to the very concept of a cell. How can you create a stable inside and outside when the liquid environment refuses to cooperate with the established rules? For years, this chemical conundrum seemed like a death sentence for the idea of the life on Titan. But science is a process of chipping away at the impossible, and in the quiet of their laboratories, a handful of planetary scientists and chemists began to dream up a solution. They asked a radical question. What if a cell on Titan wasn't made from Earth's ingredients at all? What if it constructed its walls from the very stuff of Titan's hazy atmosphere? This line of inquiry led to one of the most breathtaking concepts in astrobiology, a theoretical structure known as an azotism. The name itself is a clue: azote, the old word for nitrogen, and soma for body. It envisions a cell membrane not of lipids, but of small nitrogen-bearing organic molecules that are known to be abundant on Titan. Computer models, our virtual laboratories for testing alien worlds, became the proving ground for this audacious idea. Scientists programmed supercomputers with the laws of quantum mechanics and the brutal conditions of Titan's surface. They then introduced molecules like acrylonitrile, a compound detected in Titan's atmosphere, which on Earth is a toxic precursor to certain plastics. In the virtual methane sea, something extraordinary happened. These small nitrogen-rich molecules, which are far too rigid and insoluble to work in water, began to spontaneously self-assemble. They linked together, forming a flexible, durable and remarkably stable sheet that was the equal of our own lipid membranes. This hypothetical azotosome was a perfect mirror image of our biology. Instead of having a water-loving exterior, it had a methane-loving one, allowing it to exist in perfect harmony with its surroundings. Yet it remained a powerful barrier, creating a microscopic haven, a protected space where the complex chemistry of life could potentially unfold safe from the chaos of the outside world. It was a stunning revelation, a blueprint for a cell born not of water, but of cryogenic hydrocarbons and nitrogen. It suggested that nature on another world might not just find a different answer, but ask a completely different question, building its version of a life from materials we consider poisonous. Using a chemical language we are only just beginning to decipher, the azotosome remains a theory, a ghost in the machine, but it provides a powerful and plausible mechanism, a potential first step for building a truly alien organism from the ground up. It gives us a container, a vessel. But what would power the engine inside every living system is an engine. It must take in fuel and extract energy to maintain its structure, to grow, to reproduce, to fight against the relentless pull of entropy and decay. On Earth, the vast majority of that energy comes from a single violent chemical reaction, respiration. We breathe in oxygen, a highly reactive and aggressive element, and use it to burn the fuel we consume, primarily sugars. This process is a controlled fire, a rapid and efficient release of energy that powers our warm-blooded, fast-moving existence, the waste product carbon dioxide we exhale with every breath. This metabolic cycle is so central to our world that the search for life elsewhere has often been framed as a search for oxygen and water, the two pillars of our biosphere. But Titan has no free oxygen to speak of. Its atmosphere is a thick inert blanket of nitrogen, and its surface is saturated with compounds that oxygen would instantly incinerate. An oxygen-breathing creature on Titan would be like a creature made of gunpowder in a world of flame. It's a chemical impossibility. So if life were to exist there, it must run on a different kind of fire, a slow cold burn powered by the unique chemistry of its home. The challenge for scientists was to find a plausible metabolic pathway that could release energy in that frigid environment, using only the raw materials available in Titan's atmosphere and lakes. Again they turn their gaze to the sky. Titan's upper atmosphere is a vast chemical factory where sunlight and high-energy particles from Saturn's magnetosphere relentlessly bombard nitrogen and methane molecules. This cosmic ray bombardment shatters the simple molecules and allows their fragments to recombine into more complex and energy-rich forms. One of the most abundant byproducts of this atmospheric alchemy is acetylene. On Earth we know acetylene as a welding gas, a substance that burns with a ferociously hot flame when combined with oxygen. On Titan, this energy-rich molecule rains down from the sky like a constant gentle snowfall, dissolving into the methane lakes and settling on the surface. Here then was a potential fuel source, a celestial manna packed with chemical energy waiting to be consumed. But a fuel is useless without something to burn it with, an oxidizer in chemical terms. Without oxygen, what could play that role? The answer astrobiologists proposed was also drifting down from the sky hydrogen. While lighter gases escape from smaller worlds, Titan's immense cold and dense atmosphere allow it to retain a significant amount of hydrogen gas. The theory they developed was as elegant as it was alien. A hypothetical titanian microbe, perhaps living in the liquid methane or on the sediment of the lake bed, could take in acetylene as its food and breathe hydrogen from the atmosphere much like we breathe oxygen. It would then combine them in a metabolic reaction that is the cryogenic equivalent of our own respiration. The reaction of acetylene with hydrogen releases a significant amount of energy, enough to power the functions of a simple cell. And what would be the waste product of this strange cold fire? The end result of combining acetylene and hydrogen is simple and poetic methane. This life form would exhale the very substance that makes up its oceans. It would be breathing its world into existence, reinforcing the very environment it inhabits, in a perfect, self-sustaining chemical loop. This vision of a hydrogen-breathing, acetylene-eating organism is a masterpiece of scientific deduction a complete biological circuit designed for an alien planet. It solves the energy crisis. It uses only locally sourced materials. It is thermodynamically plausible, meaning it obeys the fundamental laws of physics and energy. But it also paints a picture of life that is almost unimaginably different from our own. The energy released by this reaction is far, far less than what earthly organisms get from oxygen. This implies that any life on Titan would have to be incredibly efficient, or more likely it would live life in the extreme slow lane. Its metabolism would be a glacial process, a biological rhythm set not to the frantic pace of a warm sunlit world, but to the patient multi-decade-long seasons of a moon in the deep freeze of the outer solar system. A thought, a movement, a single cellular division might take days or years, or even centuries of our time. It would be a life of profound patience, a slow-motion biology unfolding on geological timescales. Imagining such a creature requires us to stretch our senses to abandon our terrestrial biases about what life should look and act like. We can envision it perhaps not as a dynamic swimming fish, in our sense of the word, but as something more contemplative, more crystalline. Perhaps it would be sessile anchored to the bed of the methane sea, a living chemical reactor slowly drawing its fuel from the gentle currents. Its body built from azotosomes might not be soft and fleshy, but structured and almost mineral-like, its internal processes governed by the slow diffusion of molecules through its frigid cytoplasm. It would not see with eyes, for the light that filters through Titan's smog is faint and diffuse. It would not hear with ears, for sound travels differently in liquid methane. Its primary sense, its entire experience of the universe would be chemical. It would taste the subtle gradients of acetylene in the water, feel the presence of dissolved hydrogen, and navigate a world of pure molecular sensation. Its consciousness, if such a thing could even exist, would be utterly alien to us. How would a being whose every biological process is 1,000 times slower than our own perceive the passage of time? A single day on Titan, equivalent to 16 Earth days, might be a frantic flurry of activity. The slow drift of the hydrocarbon dunes over millennia might be the only discernible change in its landscape. It forces us to confront the possibility that the universe is filled not just with different kinds of bodies, but with different kinds of time, different modes of existence itself. This hypothetical organism is not merely a biological curiosity, it is a philosophical challenge. It suggests that life is not a single narrow solution, but a wildly adaptable principle, a chemical imperative that will find a way to manifest wherever a solvent, a membrane, and an energy source can be found. The water and carbon template we see on Earth may be nothing more than our local dialect of a universal language, one whose full grammar and vocabulary are written across the cosmos in a dazzling array of forms. We have now built in our minds a plausible blueprint for an alien. We have given it a container in the form of the azotosome. We have provided it with a source of power, the slow metabolic fire of acetylene and hydrogen. We have constructed a complete self-consistent ecosystem that could in theory exist within the crushing cold and bizarre chemistry of Titan's methane seas. This is no longer mere fantasy. It is a rigorous scientific hypothesis, a detailed and testable model of what non-water-based life might look like. It transforms Titan from a curious geological spectacle into a genuine biological prospect, a place where the most profound question we can ask might one day be answered. But a blueprint, no matter how elegant, is not the same as a building. A theory, no matter how compelling, is not the same as a discovery. The ghost we have summoned in the supercomputer must now be sought in the real world. Does any evidence exist for this strange slow-motion biology? Are there any clues hidden in the data we already possess from missions like Cassini that might point to these chemical pathways being active right now, in the dark, cold depths of Titan's alien oceans? The search for these faint biological whispers, these potential signs of a metabolism at work, is where our journey must take us next. And so, with all the ingredients seemingly in place, the complex organics, the flowing liquids, the active geology, we find ourselves standing at the shore of a dark sea filled with a breathtaking, audacious hope. We have imagined a world where the building blocks of biology are not just present, but are actively churning in a vast planetary-scale laboratory. It is a seductive vision, a second Genesis unfolding under a hazy orange sky. But just as we lean in to glimpse this alien Genesis, we collide with the first and perhaps the greatest of Titan's intractable truths. A truth so profound it governs every molecule, every reaction, and every possibility on this world. We are forced to confront the tyranny of the cold. The temperature on Titan is not merely chilly, it is a force of nature, a cryogenic vice, holding the moon in a state of suspended animation. At minus 179 degrees Celsius, or minus 290 Fahrenheit, the universe we understand begins to warp. Here on Earth, water is the medium of life, a fluid so dynamic it can carve canyons and power civilizations. On Titan, water is a rock as hard and as inert as granite. The mountains you see the bedrock beneath your feet are composed of water ice, a substance so deeply frozen it has become the geology of an entire world. The very concept of a liquid of movement of chemical interaction is pushed to its absolute physical limit. Every process is burdened by this oppressive cold, slowing to a pace that is almost geological. Think of the energy that drives life on Earth. A simple bacterium in a pond is a whirlwind of frantic activity, its internal machinery humming with thousands of chemical reactions every second. This speed is possible because Earth's temperatures provide molecules with kinetic energy, the energy of motion. They zip around, colliding, reacting, and building complexity with astonishing speed. On Titan, that energy has been bled away into the vacuum of space. Molecules are sluggish, reluctant dancers. A chemical reaction that would take a fraction of a second in Earth's oceans might in Titan's cryogenic seas take 1,000 years to complete. Or 1,000,000. This is the first great filter for life. Could an organism truly exist in a world where its own biochemistry unfolds on a timescale slower than the erosion of mountains? Imagine a creature whose every thought, every movement, every heartbeat was stretched across centuries. Its entire existence would be a slow-motion ballet, a life lived in such profound stillness that we with our frantic fire-fueled metabolisms might not even recognize it as life at all. It would be life as a glacier, not a river. This overwhelming cold doesn't just make things difficult for life as we know it, it challenges the very definition of what it means to be alive, questioning the tempo and rhythm required for existence. It forces us to ask a terrifying question. Is it possible for a world to have all the right ingredients for life, but to be simply too cold, too slow for the spark to ever truly ignite? Even if life could somehow overcome this temporal abyss, it would immediately face a second equally formidable barrier. It would have to learn to breathe in a world without breath. The air on Earth is rich with our most vital element, free oxygen. It is the fuel for our fire, the high-octane propellant that powers everything from the flight of an eagle to the firing of our own neurons. Oxygen is a ferociously reactive element tearing electrons away from other molecules in a process that releases immense amounts of energy. This process respiration is the engine of all complex life on our planet. We are creatures born of chemical fire, and we need to breathe that fire to survive. But on Titan, there is no fire. The atmosphere, a thick nitrogen-rich shroud, is almost completely devoid of free oxygen. Less than 1 part in a billion. For an Earth-based organism arriving on Titan would be like being plunged into a perfect vacuum. Suffocation would be instantaneous. Any potential Titanian life therefore cannot be like us. It cannot be based on the powerful energy-releasing reactions of oxygen. It would have to find an entirely different way to power itself, a chemistry that can function in an oxygen-starved or anaerobic environment. It would need to find an alternative to the celestial blowtorch we all carry inside us. This absence of oxygen is directly linked to the third and most fundamental challenge, the energy crisis. Life is a battle against chaos, a constant struggle to build order and complexity in a universe that favours decay. That battle requires energy. On Earth, we are drenched in it. We orbit a powerful star at a comfortable distance, and its light is captured by plants forming the base of a vast and vibrant food chain. The sun's energy flows through our biosphere like a mighty river powering every living thing. Titan orbiting nearly 10 times farther from the sun than Earth receives less than 1% of the sunlight we do. Its surface is bathed in a perpetual twilight, a dim orange glow no brighter than the moments just after sunset on Earth. This is an energetic desert. The primary source of power that drives our world is on Titan just a feeble anemic trickle. There simply isn't enough solar energy reaching the surface to directly power a widespread active biosphere in the way it does on Earth. Any life that exists there must be a master of efficiency surviving on the cosmic equivalent of crumbs. It cannot be profligate or wasteful. It must be a life of scarcity huddled around whatever meagre sources of chemical energy it can find a starved ghost haunting a world of potential. So with insufficient sunlight and a complete lack of oxygen to burn fuel, where could the energy for a second genesis possibly come from? Has nature provided another way? A hidden chemical furnace burning silently in the dark, cold depths? The answer incredibly might be yes. The solution may lie not in a powerful explosive reaction, like our own respiration, but in a far more subtle, more alien metabolic pathway. To find it, we must look at the slow, steady chemistry of Titan's atmosphere itself. High above the surface in the Moon's upper atmosphere, ultraviolet light from the distant sun, weak as it is, still has enough power to do chemistry. It strikes the abundant methane molecules, breaking them apart. The fragments, like shattered pieces of a puzzle, then recombine into more complex molecules, including one called acetylene. At the same time, this process also liberates hydrogen atoms which pair up to form hydrogen gas. Over eons, these two products, acetylene and hydrogen, have rained down from the sky, settling on the surface, and dissolving into the methane and ethane lakes. And here in the frigid, sunless depths of Kraken Mare or Legaia Mare, they represent a tantalizing possibility. A latent source of chemical energy just waiting for a catalyst to unlock it. The Aza equivalent of food and air. On paper, the reaction is simple. A molecule of acetylene can react with hydrogen gas to produce ethane, the primary component of Titan's lakes. While this reaction doesn't release the explosive burst of energy that oxygen provides, it does release some energy. A small but significant chemical profit. For a hypothetical Titanian organism, this could be the secret to life. It could be a methanogen, but of a completely alien sort. Instead of consuming carbon dioxide and producing methane like some of Earth's microbes, it would do the reverse in spirit. It would breathe hydrogen gas which is dissolved in the lakes and eat the acetylene that falls from the sky. Its waste product would be the very liquid it swims in, ethane. It would be a creature perfectly, beautifully adapted to its environment, its entire metabolism built from the most abundant materials at its disposal. Its existence would be a quiet, elegant chemical loop powered by the leftovers of ancient sunlight from the upper atmosphere. This theoretical metabolism, first proposed by astrobiologists Chris McKay and Heather Smith, provides a plausible, scientifically grounded pathway for life on Titan. It solves the energy problem without sunlight and without oxygen. But it also reinforces the immense challenges we've already seen. The energy released by this acetylene-hydrogen reaction is pitifully small compared to what we're used to. It's about 40 times less powerful than the aerobic respiration that powers you and me. This means that any life powered by it would by necessity be extraordinarily slow. Its metabolism would not be a roaring fire, but the barest of embers, a metabolic whisper in the profound silence. And this leads us to the final daunting hurdle. If this slow, strange, alien life exists, how in the cosmos would we ever find it? Our search for extraterrestrial life has until now been designed around our own image. We look for the chemical signatures of Earth-like respiration. We look for fast-acting biological processes. We look for organisms that consume and excrete at a pace we can measure in a lab. The instruments aboard our Mars rovers, for example, are designed to detect the byproducts of relatively rapid microbial activity. But applying these methods on Titan would be like trying to detect the movement of a continent with a stopwatch. A creature living on the razor-thin energy margins of the acetylene reaction would be fundamentally different. It might be incredibly small, perhaps not even cellular in a way we would recognize. Its movements might be non-existent to our eyes, its growth rate measured in centuries. Its entire population spread across a vast dark sea might only consume a few tons of hydrogen and acetylene over thousands of years. The chemical signature, the biosignature, it would leave behind would be so faint, so subtle, that it could be easily mistaken for a non-biological chemical process or simple statistical noise. We would be searching for a whisper in a silent cathedral, The very nature of this potential life makes it almost impossible to detect with our current technology. Imagine sending a submarine into Kraken Mare. What would it look for? There would be no schools of alien fish swimming past the camera. There would be no forests of kelp-like organisms swaying in the methane currents. We might not even find individual microbes. The life could be a diffuse, slow-reacting chemical film coating the pebbles on the seafloor. It could be a loose colony of molecules, a living sludge hibernating at the bottom of a river delta, waking for a brief period of activity every few millennia. Its biological processes would be so glacial that a sample brought into the sterile environment of a lander's laboratory might appear completely inert. We could be holding alien life in our robotic hands and be utterly incapable of recognizing it for what it is. To find it, we would need to invent entirely new methods of observation. We would need instruments capable of measuring infinitesimally small energy gradients over vast areas. We would need missions that could sit patiently for decades, watching for minute, almost imperceptible changes in the chemical composition of a single patch of lake bed. We would need an artificial intelligence that could distinguish the signature of a slow, biological network from the random hum of geology and atmospheric chemistry. We are in a very real sense not yet equipped to find the very life we are searching for. We are confronted with a staggering paradox. The very conditions that might allow a truly alien form of life to emerge on Titan, the extreme cold, the exotic solvents, the low-energy chemistry, also conspire to hide it from us, cloaking it in a veil of stillness and subtlety. The challenges are immense, a series of great filters that seem at first glance almost insurmountable. The cold slows down time itself. The lack of oxygen starves the world of fire. The feeble sunlight offers little energy to build with. And the very life that might thread this impossible needle would be so quiet, so slow, so fundamentally different from us, that it may as well be a phantom. Yet we are not deterred, because within each of these great challenges lies a hidden clue, a new direction for our search. The brutal cold necessitates a new biochemistry, one whose secrets could rewrite our textbooks. The absence of oxygen forces us to imagine metabolisms that run on novel fuels like hydrogen and acetylene. And the daunting difficulty of detection is not a dead end but an invitation. It is an invitation to be more creative, more patient, and more imaginative in our exploration of the cosmos. It tells us that to find the alien, we must first abandon our earthbound assumptions and learn to look at the universe with new eyes, preparing ourselves to recognize a form of life so patient and so quiet it has remained hidden in plain sight. The question is no longer just whether life is there, but whether we are clever enough to see it. And to answer that, we must build a new kind of explorer, one capable of venturing into this cryogenic ocean and listening for its glacial heartbeat. And so, the grand chemical equation of Titan remains unbalanced, a tantalizing puzzle, whispered across 1 billion miles of void. The clues scattered in the haze and hinted at by the strange absence of hydrogen at its surface demand a different kind of response. Passive observation from orbit or a single fleeting glimpse from a falling probe is no longer enough. To solve a mystery of this magnitude, we cannot simply be astronomers. We must become detectives on the ground. We must send an emissary, a proxy for our own senses capable of navigating this alien landscape, not as a visitor but as an inhabitant. The time has come to unmoor ourselves from the static lander, a concept that has served us from the moon to Mars, and embrace a radical new form of exploration. The time has come for us to fly on another world. What we are sending is not just a machine, it is an incarnation of human ingenuity, an audacious dream given form and function. We call it Dragonfly. The name is no mere poetry. It is a promise. A quadcopter the size of a small car powered by the slow, steady decay of plutonium, this magnificent rotorcraft is designed to do what was once the exclusive domain of science fiction. It will rise from the surface on 8 contra-rotating blades, a nuclear-powered insect buzzing through the thick nitrogen-rich air. It will fly for miles, leapfrogging from one scientific treasure to the next, landing gently on its skids to taste and touch and listen. It will become the first mobile aerial laboratory on an extraterrestrial world. For over a decade, Dragonfly will perform dozens of these carefully choreographed sorties, mapping a world where the very air and ground are made of substances we consider exotic. It is a quantum leap in planetary exploration, a mission profile born from the unique physics of Titan itself. The atmosphere here is 4 times denser than Earth's, and the gravity is a mere 1/7 of our own. These conditions, which would be a crushing liability on Mars, are a gift on Titan. Here, flight is easy. Here, a Dragonfly can soar. Its journey begins with a fiery launch from Earth, a departure that marks the culmination of decades of research and engineering. For years, it will slumber through the cold dark of interplanetary space, a silent promise, rocketing towards the outer solar system. Upon arrival, it will face the trial that has claimed so many other missions, the harrowing descent. Encased in an aeroshell, it will plunge into Titan's orange atmosphere at hypersonic speeds, a man-made meteor streaking through skies of smog. Heat shields will glow, parachutes will billow, and then at the critical moment the shell will fall away, releasing the explorer within. Dragonfly will fire its rotors, stabilizing itself in the alien winds, and begin a controlled, powered descent to a world we have only ever seen in broad strokes. Its target landing zone is a masterstroke of scientific selection, a place where all of Titan's key mysteries converge. It is not the famous methane seas, not yet. The risks of landing in an unknown liquid are too great. Instead, Dragonfly will set down near the Selk impact crater, a region of staggering geological diversity. Imagine this landscape through Dragonfly's own cameras. Before you lie vast, rippling fields of organic sand dunes blacker than coal, sculpted by alien winds into shapes both familiar and strange. These are not dunes of silica like the sands of the Sahara, but grains of solid hydrocarbons that have precipitated from the atmosphere over untold eons. They're a vast repository of prebiotic chemistry, a dark library whose pages we're about to read. In another direction, the crater itself looms a 50-mile-wide scar on the face of Titan. This is not just a relic of ancient violence. It is a place of immense promise. The cataclysmic energy of the impact occurring sometime in the last few 100 million years would have melted the water ice crust, creating a transient pool of a substance exquisitely rare on Titan's surface liquid water. For thousands of years, perhaps longer, this hydrothermal basin would have been a warm, swirling cauldron where the complex organics from the dunes and the atmosphere could mix and react with liquid H2O. It is by our current understanding the single most likely place in the entire solar system beyond Earth to find the chemical precursors to life, or perhaps something more. And threaded through this landscape are the sinuous braided channels carved not by water, but by flowing methane remnants of past floods that hint at a dynamic, evolving world. This is Dragonfly's playground, its laboratory, its hunting ground. To conduct its investigation, Dragonfly is armed with a suite of instruments so sensitive they represent the pinnacle of miniaturized analytical science. This is not a blunt instrument. It is a surgical tool designed to dissect the very soul of Titan's chemistry. Its primary weapon in the search for life is the Dragonfly Mass Spectrometer, or DRAMS. After landing at a promising site, a drill on each of the lander's skids will whir to life, biting into the frozen ground to collect samples of the organic regolith. These precious grains of another world will be pneumatically conveyed into the heart of the machine, into an oven that will gently heat them. As the complex organic molecules vaporize, they are fed into the mass spectrometer, an instrument that acts as a kind of chemical weigh station. It bombards the molecules with a laser, breaking them into charged fragments, and then measures the mass of each piece with breathtaking precision. From this data, scientists back on Earth can reconstruct the original molecules, identifying them with unambiguous certainty. DRAMS is searching for the alphabet of life. Is it seeing simple molecules like amino acids, the building blocks of proteins, or nucleobases, the rungs on the ladder of DNA and RNA? The discovery of these molecules alone would be monumental, confirming that the primordial soup on Titan is even richer than we imagined. But DRAMS is designed to look for something far more subtle, a clue so profound it could stand as a nearly definitive biosignature. It will be searching for a ghost in the molecular machine, a phenomenon known as chirality. Many of the complex molecules of life, like amino acids, are chiral. They can exist in two forms that are mirror images of each other, like your left and right hands. They are chemically identical but structurally distinct. Non-biological processes tend to create these molecules in a roughly equal 50-50 mixture of left-handed and right-handed versions, but life, for reasons we still don't fully understand, is remarkably picky. Life on Earth in its every form, from the simplest bacterium to the cells in your own body, exclusively uses left-handed amino acids to build its proteins. This overwhelming preference, known as homochirality, is a universal hallmark of terrestrial biology. If DRAMS were to analyze a sample from the Selk crater and find that the amino acids within showed a significant bias, say 90% were right-handed instead of an even split, it would be an electrifying discovery. Such an enantiomeric excess is exceptionally difficult to explain through random geology or atmospheric chemistry. It would be the chemical echo of a selective metabolic process. It would be the fingerprint of life. But Dragonfly's senses extend far beyond what it can taste. To understand the world beneath its feet, it carries the Dragonfly Gamma Ray and Neutron Spectrometer, or DRAGNS. This instrument is Dragonfly's subsurface vision. It doesn't need to drill to see what lies below. Instead, it listens. The surface of Titan is constantly bombarded by high-energy cosmic rays from deep space. When these rays strike the nuclei of atoms in the ground, those nuclei emit their own characteristic gamma rays and neutrons. DRAGNS is a highly sensitive detector that can capture this faint radiation, analyzing its energy spectrum to determine the elemental composition of the ground down to a depth of several feet. It can distinguish between carbon, nitrogen, oxygen, and hydrogen, painting a detailed map of the bulk chemistry of Titan's crust. Its primary mission is to search for the telltale signature of water ice, the bedrock of this world hidden just beneath the organic blanket. Knowing the depth and concentration of this ice is crucial, as it tells us how accessible the key ingredient of water might have been to the surface organics. DRAGNS will reveal the hidden geologic context for any chemical discoveries DRAMS makes, turning a simple sample analysis into a rich, three-dimensional story of the landscape's history. To truly understand Titan, however, you must understand its weather. The winds that shape the dunes, the pressure that governs the state of methane, the humidity that signals an impending methane storm, all of these are critical pieces of the puzzle. The Dragonfly, Geophysics and Meteorology package. DRAGMET will be the mission's nerve endings constantly feeling the pulse of the environment. A suite of sensors will measure air and surface temperature pressure, wind speed and direction, and even the electric field of the atmosphere. On every flight and during every moment on the ground, DRAGMET will be building the first long-term weather record from the surface of Titan. This data provides the vital context for everything else Dragonfly does. It will help mission planners decide when and where it is safe to fly. It will inform the interpretation of the chemical samples, revealing how the modern atmosphere might be interacting with the ancient surface. DRAGMET will even deploy a seismometer at each landing site, listening for the faint tremors of Titan quakes. These vibrations could reveal the thickness of the ice shell and perhaps even provide evidence for the global subsurface ocean of liquid water we believe sloshes far below. We are not just exploring a surface, we are investigating a whole living planet, and DRAGMET will be our guide to its dynamic and often violent personality. And of course, Dragonfly will be our eyes. The DragonCam suite of cameras will deliver images of a quality that will redefine our vision of this world. A panoramic camera mounted high on a mast will capture sweeping vistas of the alien landscape after each landing, allowing geologists to read the story of the terrain and select the most promising targets for the next flight. A pair of forward-looking cameras will act as the pilot's eyes during flights scouting the path ahead. But perhaps most exciting are the microscopic imagers. One will be positioned to view the ground directly beneath the lander, giving us an ultra-high-resolution view of the texture and structure of the organic sediments. Another will examine the samples collected by the drills before they are sent to the mass spectrometer. For the first time, we will see the grains of Titan soil. Are they sharp or rounded? Are they uniform, or is there a variety of colours and textures? These microscopic details are a form of language, and DragonCam will give us the ability to read it, providing visual evidence to complement the hard chemical data. We will not just know what Titan is made of, we will see it in all its breathtaking intimate detail. This then is the grand strategy. A flight, a landing, a comprehensive survey of the new location with cameras and meteorological sensors, a deep probe of the subsurface composition with the neutron spectrometer, and then the critical moment, the selection and drilling of a sample. The careful delivery of this alien material into the heart of the machine for the ultimate chemical interrogation by the mass spectrometer. The mission plan calls for this sequence to be repeated dozens of times, at dozens of unique locations, creating a traverse that will stretch for over 100 miles. Each landing site will be chosen based on the discoveries of the last dynamic and responsive exploration campaign guided by real-time science. Dragonfly will hop from the dark organic dunes to the rugged ejector blanket of the Selk crater. It may venture to the crater floor itself, searching for the altered chemistry left behind by the ancient impact melt. It could fly to the edge of a channel carved by liquid methane sampling the sediments left by a long-vanished river. Each hop is a new chapter. Each sample is a potential revelation. We are searching for biosignatures, but not as we know them. We are not looking for fossils or bones. We are looking for a subtle perversion of chemistry. We are searching for an unlikely concentration of certain complex molecules, a pattern that defies the lazy randomness of abiotic nature. We are looking for that telltale chiral signature, the ghostly preference for one molecular hand over the other. We are hunting for chemical disequilibrium, a state where certain chemicals are more or less abundant than they should be, suggesting that some unseen process, some metabolic engine, is actively consuming them or excreting them as waste. This is the search for life at its most fundamental level, as a force that imposes order on chaos that bends the rules of chemistry to its own will. Dragonfly is not just a geological mission, it is a mission of astrobiological espionage designed to uncover the secret workings of an alien world. It will land and it will drill into the frozen earth. It will heat the sample, and the vaporized molecules will begin their journey into the detector. On a computer screen in a clean room back on Earth, a series of peaks will begin to appear. A spectrum, a chemical fingerprint taken from a distance of over 1 billion miles. And as our scientists work to decipher that code, a profound silence will grip the room. For in that data, in that complex series of spikes and valleys may lie the answer. Not just about Titan, but about the universe, and our lonely place within it. The quest for the alien fish of Titan's methane seas is no longer a theoretical exercise. The hunt has begun. The dragonfly is on its way, and so we stand at the culmination of a journey that has carried us across 1 billion miles of darkness. We have travelled from a time when Titan was little more than a veiled secret, a smudge of light in Christian Huygens' primitive telescope, to this present moment of profound and imminent revelation. The story of this world has been one of peeling back layers, not just of its own dense nitrogen-rich atmosphere, but of our own preconceptions. Each layer removed has unveiled a landscape more alien yet more strangely familiar than we could have ever dared to imagine. It began as a point of frustration, a world that stubbornly hid its face, a tantalizing mystery, wrapped in an orange shroud. For centuries it remained just that, a celestial enigma whose surface was a blank canvas for speculation and fantasy. Then came the pioneers, the robotic emissaries we sent out into the cold and the dark. Pioneer 11 gave us our first tentative glance, confirming its frigid nature and its thick, impenetrable haze. The Voyager spacecraft followed their flybys, painting a slightly clearer, yet still featureless portrait of a world-sized chemical factory, a place where the building blocks of life were being cooked up on a planetary scale. These were tantalizing hints, whispers of a world far more complex than a simple ball of ice and rock. But the true revelation, the moment our understanding of the solar system was irrevocably fractured and reformed, arrived with Cassini. For 13 years, that tireless nuclear-powered explorer orbited Saturn, a devoted scholar to the ringed planet and its court of moons. And in Titan, it found its magnum opus. With radar that could pierce the unyielding haze, it began to paint a map of a world we had never truly seen. What it uncovered was not a monotonous wasteland of ice, but a vibrant dynamic landscape sculpted by forces we recognized, yet driven by chemistry we did not. There, etched into the frozen crust, were vast continent-sized plains of organic sand dunes, sculpted by alien winds into shapes that mirrored the deserts of Earth. There were towering mountain ranges, their peaks likely made of water ice as hard as granite thrust upwards by cryovolcanic pressures from a liquid ocean buried deep beneath the surface, and then the discovery that changed everything. The radar beams bounced back not from solid ground, but from something perfectly unnervingly flat. Something liquid. Lakes, rivers, seas. Not of water, the life-giving solvent of our own world, but of liquid methane and ethane hydrocarbons chilled to a staggering minus 180 degrees Celsius. We saw river deltas intricate and branching identical in form to the Nile or the Mississippi, but carved by a substance that on Earth is a flammable gas. We saw shorelines, bays and islands dotting the surfaces of Kraken Mare and Ligeia Mare, their placid expanses reflecting a faint ghostly light from Saturn. The arrival of the Huygens probe was the crescendo of this initial exploration, a moment of unprecedented intimacy. As it descended through that thick, soupy atmosphere, it gave us our first and only direct taste of this world. It heard the winds, it measured the chemical soup, and for a few precious hours it showed us a view from the surface, a floodplain of rounded water ice pebbles smoothed by the flow of liquid methane resting under a dim apricot-coloured sky. It was a scene of profound and desolate beauty, the confirmation of a complete active liquid cycle on another world. A hydrological cycle, but with hydrocarbons. Titan had declared itself not merely a moon, but a world in its own right, a dark mirror to our own planet governed by a set of rules we were only just beginning to comprehend. This transformation from a hazy dot to a world, with weather seasons and oceans, represents one of the greatest exploratory triumphs in human history. But its true significance lies not in the geography it revealed, but in the philosophy it shattered. For all of our history, our search for life beyond Earth has been governed by a powerful, deeply ingrained piece of logic. A simple mantra, follow the water. It was the foundational assumption of astrobiology, the bedrock upon which our entire search for extraterrestrial life was built. Water is the universal solvent, the medium for every biological process we have ever known, from the smallest bacterium to the largest whale. Its unique chemical properties make it the perfect cradle for the complex dance of molecules that we call life. Our telescopes scoured the heavens for planets in the Goldilocks zone, that narrow temperate band around a star where liquid water could persist on a world's surface. We sent rovers to Mars to search for the ghosts of ancient oceans and dried-up riverbeds, seeking evidence that our neighbour once shared our most precious resource. The logic was sound, born from the only example of life we had. But it was also a form of cosmic chauvinism, an intellectual cage forged from our own biology. We were like a deep-sea fish convinced that life could only exist in the crushing pressure and darkness of the abyss, unable to conceive of the sunlit world above. Titan smashed that cage. It presented us with a reality so profoundly challenging, so utterly contrary to our expectations, that it forced a fundamental schism in our thinking. Here was a world that was an active, vibrant, and geologically complex place, not despite its lack of liquid water, but precisely because of its abundance of another liquid. It offered us a compelling, tangible alternative. A world where liquid methane plays the role of water, where it carves the canyons, fills the seas, and falls as rain from the sky. This realization was more than just a scientific discovery. It was an act of philosophical liberation. It told us that our definition of a habitable world was not a universal law, but merely a local ordinance. The universe, it seemed, was far more creative and less constrained by our Earth-centric rulebook than we had ever believed possible. Titan whispered to us that the conditions for life might not be a narrow, singular path, but a vast branching tree of possibilities. And if liquid methane could form a stable environment with active geology and a rich supply of complex organic molecules, then what other liquids could do the same? Could life arise in the supercritical carbon dioxide clouds of a distant exoplanet, or in the ammonia water slurries we suspect exist deep within ice giants? Titan cracked open the door to a universe teeming not just with worlds, but with potential biologies, with architectures of life so fundamentally different from our own they would seem like magic. It compels us to ask a question that cuts to the very core of our understanding of existence. What truly is life? Is it intrinsically tied to DNA, to water, to the specific carbon-based chemistry that animates every living thing on our planet? Or is that just one local expression of a much more fundamental cosmic principle? Perhaps life is not a specific set of molecules, but a process. A process of capturing energy, of storing information, of replicating and adapting to an environment. If that is the case, then the cryogenic seas of Titan are not a barren toxic wasteland, but a potential cradle for a second genesis. Imagine for a moment what that life might be like, swimming not in water but in liquid natural gas. It would not be life as we know it. It couldn't be. The brutal cold that would freeze us solid in an instant would be to these organisms a balmy life-giving environment. Oxygen, the very air we breathe, would be a violent corrosive poison to their delicate chemistry. Their cells, if they even have cells, would not be wrapped in the fatty lipid bilayers that protect our own. Those membranes would shatter like glass in the Titanian cold. Instead, scientists have theorized the existence of azotosomes membranes built from nitrogen-based organic compounds that would remain flexible and stable in liquid methane. A biological architecture utterly alien to our own. Their metabolism would be a slow patient fire, a stark contrast to the frantic energy consumption of life on Earth. In the dim light and freezing temperatures, chemical reactions unfold over vast timescales. A Titanian creature might experience time differently, its life unfolding like a slow-motion ballet, a single thought or movement taking what would be minutes or hours for us. They would be beings of profound patience born from the cold and the dark. How would such a life form store its genetic information without DNA or RNA, which require water to function? What molecular structure could carry the blueprint for replication? Perhaps it would be based on silicon polymers or other exotic chemistries that thrive in the frigid hydrocarbon soup. The answer is we simply do not know. We are standing at the shoreline of an unknown ocean, guessing at the nature of the creatures that might swim in its depths. Every hypothesis, every computer model is an act of imagination, an attempt to think beyond the confines of our own biology. This is Titan's greatest gift to us. It has taken the question, "Are we alone?" and transformed it into 1,000 more. What are the limits of biology? What are the universal requirements for life? And what are merely the parochial customs of our own planet's biochemistry? This is the true purpose of the Dragonfly mission. Yes, it is a search for life, a quest for biosignatures in the organic sands of the Celt crater. But its mission is grander than just finding alien microbes. Dragonfly is a search for a second data point. For our entire existence, we have studied a single tree of life, one that sprouted on Earth billions of years ago, and branched into the magnificent diversity we see today. But it is still just one tree, one origin. If Dragonfly discovers life on Titan, even the simplest, most primitive form of life, and can confirm that it arose independently from life on Earth, it will be the single, most profound discovery in the history of science. A second genesis would prove that life is not a fluke, not a one in a trillion cosmic accident that happened only here. It would mean that life is a fundamental property of the cosmos. It would imply that the universe is hardwired for biology, that wherever the conditions are right, whatever those conditions may be, the spark of life can ignite. The stars above would be transformed from distant sterile points of light into a galaxy of potential ecosystems, a celestial chorus of living worlds. The silence we have heard for so long would not be evidence of absence, but merely of a language we do not yet understand. But what if Dragonfly finds nothing? What if it drills into the ice samples, the organic ooze, and finds only complex, fascinating chemistry, but no biology? Would the journey have been a failure? Absolutely not. The absence of evidence can itself be a powerful form of evidence. If a world like Titan, with all its ingredients, a thick atmosphere, a stable liquid medium, an abundance of complex organic molecules, and a source of energy is ultimately sterile, that would tell us something equally profound. It would suggest that the bridge from complex chemistry to simple biology, the process of abiogenesis, is an incredibly difficult and rare step. It would make the life on our own planet seem even more precious, more miraculous. A fragile flame flickering in an immense and indifferent darkness. Either outcome, life or no life, fundamentally alters our understanding of our place in the cosmos. There is no mundane result. When that quadcopter finally touches down on the alien sands of Titan, it will be more than a machine. It will be the physical embodiment of our deepest, most human questions. It will be our eyes, our hands, and our laboratory, the extension of our own relentless curiosity. We send it not just to find answers for ourselves, but for every human who has ever lived and looked up at the night sky in wonder. From the first hominid who recognized the patterns in the stars to the ancient Greek philosophers who debated the existence of other worlds to the astronomers who first turned their telescopes towards Saturn. Dragonfly carries all of their dreams and questions with it. The story of Titan is in the end a story about us. It reflects our own journey of discovery, our capacity to be humbled, and our willingness to discard cherished beliefs in the face of new evidence. It has forced us to expand our imagination to think more creatively, and to embrace the possibility that we are but one small part of a universe far stranger and more wonderful than we have yet conceived. This distant frozen moon has become a cosmic anchor for our hopes and a powerful symbol of the unknown. It serves as a constant humbling reminder that the universe is under no obligation to conform to our expectations. Its creativity is boundless, its potential for novelty infinite. Life, if it exists elsewhere, may not come in forms we anticipate or even recognize. It may not be carbon-based. It may not live in water. It may not communicate with radio waves or build civilizations. It might be a slow, crystalline intelligence living in a methane sea. It might be a collective consciousness adrift in the clouds of a gas giant. It might be something our science has not even developed the language to describe. Titan teaches us that the cosmos is not just a stage for one play. It is a grand theatre with 1 billion stages each potentially hosting its own unique and extraordinary drama. And so, as we look up at the night sky, our perspective has been forever changed. We no longer see just empty space between the stars. We see a realm of possibility. We see the cold moons of Jupiter and Saturn not as barren wastelands, but as potential homes for chemistries we do not understand. We see the thousands of exoplanets discovered in recent years not just as data points on a graph, but as worlds, each with its own story, its own potential for wonder. Titan has bequeathed to us a universe re-inspired, a cosmos, filled once again with mystery and with the plausible hope of discovery. It challenges the lingering fear of our own cosmic solitude, replacing it with a sense of profound, exhilarating anticipation. We are living in an age when the question of life beyond Earth has moved from the realm of fiction into the realm of testable science. And Titan, that beautiful, hazy, hydrocarbon-drenched world, is on the front line of that quest. Whatever Dragonfly finds or does not find, our journey there has already succeeded. It has succeeded because it has expanded the human mind. It has pushed us to the very limits of our understanding and beckoned us to step beyond. And it has left us here on the shores of our own warm, watery world, staring out into the grand, silent ocean of space, knowing that it is not empty. It is full of worlds, and in that knowledge we find not an answer, but a more beautiful question, and an invitation to continue the search.